Have you ever looked up at the stars and wondered what it would be like to zip between them at the speed of light? You're not alone. This question has captivated humanity since we first understood that light has a speed limit. But here's the thing. The answer isn't what science fiction movies have taught us. It's far stranger, more mind-bending, and ultimately more beautiful than any Hollywood script could imagine. You see, when Albert Einstein first proposed his theory of special relativity in 1905, he didn't just change physics. He revealed that the universe has built-in rules that make light speed travel not just difficult, but fundamentally different from anything we experience in our daily lives. One quick question: if aliens are watching us right now, what do you think they're thinking about humanity? Comment down below. I will pin the most creative answer. Let's start our journey by understanding why light speed is so special. In the universe, there's a fundamental relationship between space and time. They're not separate things, they're woven together into what physicists call spacetime. And light speed isn't just the speed of light, it's the speed of causality itself, the maximum rate at which cause and effect can propagate through the universe. Imagine space-time as a vast cosmic fabric. Everything with mass creates a dent in this fabric. That's what we experience as gravity. But there's a speed limit built into the very structure of this fabric. It's not that the universe has a rule saying nothing can go faster than light. Instead, light speed is the natural speed at which massless things move through space-time when nothing is slowing them down. This is why photons, particles of light, always travel at light speed in a vacuum. They have no mass, so nothing holds them back from moving at the universe's maximum speed, but you have mass, and that changes everything. As you accelerate toward light speed, something remarkable happens. From your perspective, you're just speeding up like normal. You feel the acceleration pushing you back into your seat, just like in a fast car or airplane. But to someone watching from Earth, you're not just moving through space, you're also moving through time differently. This isn't science fiction. It's a scientific fact confirmed by countless experiments. In 1971, physicists Haffel and Keating flew atomic clocks around the world on commercial airliners. When they compared these clocks to identical ones that stayed on the ground, they found exactly the time difference Einstein's equations predicted. The flying clocks had aged slightly less than the stationary ones. But that's just airplanes moving at a few hundred miles per hour. What happens as you approach the cosmic speed limit? The effects become exponentially more dramatic. At 50% light speed, time dilation is noticeable but not extreme. Your clock would run about 13% slower than Earth clocks. But at 90% light speed, your clock would run at less than half the speed of Earth clocks, and at 99.9% light speed, your clock would tick 44 times slower than those on Earth. This means if you traveled to Proxima Centauri, our nearest star at 4.24 light-years away, at 99.9% light speed, the journey would take about 4.24 years from Earth's perspective. But for you, you'd experience only about 35 days. You'd arrive at another star system having aged just over a month, while everyone on Earth aged over 4 years. The closer you get to light speed, the more extreme this effect becomes. At 99.9999% light speed, a journey to the center of our galaxy 26,000 light-years away would take 26,000 years from Earth's perspective. But you'd experience it for just under 4 years. You could travel to the Andromeda galaxy, 2.5 million light-years away, and experience the journey as taking only about 35 years of your life, while Earth experienced 2.5 million years passing. This is the first mind-bending reality of light-speed travel. It's a one-way ticket to the future. There's no way to come back to the same time you left. If you took that trip to Andromeda and back, you'd return to an Earth 5 million years in the future. Everyone you knew would be long gone. Humanity itself might have evolved into something unrecognizable or perhaps wouldn't exist at all. But wait, we're getting ahead of ourselves. Before you can experience these mind-bending time effects, you first have to accelerate to near light speed. And this is where the universe throws up its first major roadblock, one that makes reaching light speed not just difficult, but literally impossible for anything with mass. You see, as you accelerate, something strange happens to your mass. Not your rest mass, the mass you have when you're sitting still, that stays the same. But your relativistic mass, the mass you have when you're moving, increases. And it doesn't increase linearly, it follows a curve that physicists call the Lorentz factor, named after Hendrik Lorentz, who first derived these equations even before Einstein. At everyday speeds, this effect is so tiny, it's unnoticeable. When you're driving at 60 miles per hour, your relativistic mass has increased by less than 0.5%. But as you approach light speed, this increase becomes dramatic. At 50% light speed, your mass is about 15% greater. At 90% light speed, you're more than twice as massive. At 99% light speed, you're 7 times more massive. And here's the kicker. The closer you get to light speed, the more energy it takes to accelerate even a tiny bit more. It's like trying to push a car that gets heavier with every inch you move it. At first, it's easy, then it gets harder, then it becomes nearly impossible. And at light speed itself, the equations tell us your mass would become infinite, requiring infinite energy to accelerate. Let's put this in perspective with real numbers from actual particle accelerators. At CERN's Large Hadron Collider, the most powerful particle accelerator ever built, protons are accelerated to 99.999991% of light speed. That's incredibly close to light speed. These protons are moving so fast that they travel around the 17-mile circumference of the LHC 11,000 times per second. But here's what's remarkable. To accelerate a single proton, a particle so small that about 1 billion trillion of them would fit on the head of a pin, to this speed requires giving it the kinetic energy of a mosquito in flight. That might not sound like much, but remember, we're talking about a single subatomic particle. The energy density is enormous. Now imagine trying to accelerate something with real mass, like you, to similar speeds. Let's say you weigh 150 pounds or about 68 kilograms. To accelerate you to just 90% light speed would require about 1.7 times 10 to the 18th joules of energy. That's roughly the total energy consumption of the entire United States for 6 months. And that's just to reach 90% light speed. To reach 99% light speed, you'd need about 7 times more energy, 99.9%. Now we're talking about the total energy output of the Sun for about 2 seconds. And to actually reach light speed, the equations are clear, it would require infinite energy, not just a lot, not just more than we can produce. Literally infinite. This is why physicists say that light speed is a cosmic speed limit. It's not that there's a universal traffic cop stopping you, it's that the very structure of space-time makes it impossible for anything with mass to reach light speed. The universe is essentially telling us you can get close, but you can never quite get there. But let's imagine for a moment that we could somehow overcome this energy problem. Maybe we discover some exotic new physics, or tap into zero-point energy, or find a way around Einstein's equations. What would the journey actually feel like? First, let's talk about acceleration. The human body can only handle so much. Fighter pilots with special suits and training can handle about 9 Gs, 9 times Earth's gravity, for short periods. Without special equipment, most people black out around 5 Gs. For a comfortable long-term journey, you'd want to limit acceleration to about 1 G, the same as Earth's gravity. At 1 g of constant acceleration, it would take about 354 days to reach 90% light speed. To reach 99% light speed would take about 2 years, and to reach 99.9%, you'd be accelerating for over 6 years. Remember, the closer you get to light speed, the harder it becomes to accelerate further. But here's where time dilation plays a fascinating role. From your perspective on the ship, you're not just accelerating through space, you're accelerating through time. As your speed increases and time dilation kicks in, you actually experience less time during the acceleration than observers on Earth would measure. This creates an interesting possibility. If you could maintain 1 g acceleration indefinitely, a big if, given the energy requirements, you could travel anywhere in the observable universe within a human lifetime, at least from your perspective. Accelerating at 1 g for about 20 years of ship time would take you to the edge of the observable universe, some 46 billion light-years away. Of course, Earth would experience billions of years passing during your journey, but acceleration brings its own challenges beyond just energy. As you approach light speed, the universe itself begins to look different. This brings us to one of the most visually spectacular effects of relativistic travel: the aberration of light. Imagine you're in your spacecraft accelerating toward light speed. You might expect to see stars whizzing past like in science fiction movies, but that's not what happens at all. Instead, something far stranger occurs. Due to an effect called relativistic aberration, the stars appear to shift position. Stars that were behind you seem to move to the sides and then toward the front. As you approach light speed, more and more of the universe appears to compress into a bright circle directly ahead of you. This isn't an optical illusion. It's a real consequence of how light behaves at relativistic speeds. The Hubble Space Telescope and other instruments have observed this effect in jets of material ejected from black holes at near light speed. The jets appear brighter when pointed toward us due to relativistic beaming, a related phenomenon. At 90% light speed, you'd see about half the sky compressed into a 60-degree cone in front of you. The stars behind you would appear dimmer and shifted toward the red end of the spectrum, while stars ahead would be brighter and shifted toward blue. At 99.9% light speed, almost the entire visible universe would be compressed into a blindingly bright disk just 25 degrees wide directly ahead. But the visual effects go even deeper than this. The Doppler effect, which you might know from the way ambulance sirens change pitch as they pass by, becomes extreme at relativistic speeds. Light from stars ahead of you gets compressed to shorter wavelengths, blue shifted, while light from behind is stretched to longer wavelengths, red shifted. At extreme speeds, this shift is so dramatic that visible light from stars ahead would shift into the ultraviolet, X-ray, and even gamma-ray range. Stars behind you would shift into the infrared and radio waves. You'd need special sensors to see anything at all. The familiar constellations would be completely unrecognizable, compressed and distorted beyond recognition. Speaking of the cosmic speed limit, you might be wondering why this barrier even exists in the first place. I actually explored this fascinating question in my video, Why Nothing Can Go Faster Than Light Speed, and the answer isn't what you'd expect. It turns out light speed isn't really about light at all, but about the fundamental structure of reality itself. Check it out after this video to discover why the universe absolutely must have this speed limit to exist. The link is in the description and on the card above. Now, back to our exploration. Recent simulations by astrophysicists using data from the Gaia Space Telescope, which has mapped over 1 billion stars in our galaxy, show exactly what this would look like. As you approach light speed, the entire Milky Way would appear to wrap around and compress into that bright disk ahead of you. It's beautiful and terrifying at the same time. And then there's the issue of interstellar medium. Space isn't empty. Even in the vast voids between stars, there are about 1 or 2 hydrogen atoms per cubic centimeter. At normal speeds, these are harmless. But at relativistic speeds, they become deadly radiation. When you're traveling at 99.9% light speed, those harmless hydrogen atoms hit your spacecraft with the energy of high-speed bullets. Each proton strikes with about the same energy as a proton in the Large Hadron Collider. Your spacecraft would need massive shielding, probably several meters of dense material, just to protect you from the interstellar medium. But even with perfect shielding, there's another problem. As you plow through space at near light speed, you're essentially creating your own particle accelerator. The collisions between your ship and interstellar particles would create showers of secondary particles and radiation. It would be like flying through a constant storm of cosmic rays. NASA's Voyager probes, traveling at a mere 0.006% light speed, have given us valuable data about the interstellar medium. They've shown that space between stars is more complex than we thought, with magnetic fields, cosmic rays, and varying densities of particles. All of these would become serious hazards at relativistic speeds. If you're still with me on this incredible journey through relativistic physics, it would mean the world to me if you could hit that subscribe button and give this video a thumbs up. I'm just starting out on this cosmic adventure of sharing the wonders of the universe with you, and your support helps me reach more curious minds like yours. Every subscription tells me that there are people out there who share my passion for exploring the deepest mysteries of existence. Now let's dive into something even more mind-bending. What happens to space itself when you travel at near light speed? You see, Einstein's special relativity doesn't just tell us that time slows down, it also tells us that space contracts. This phenomenon, called length contraction or Lorentz contraction, is just as real as time dilation, and it would fundamentally alter your experience of the universe. From your perspective on a spacecraft traveling at near light speed, the universe in your direction of travel literally becomes compressed. At 50% light speed, distances shrink to about 87% of their original length. At 90% light speed, everything is compressed to just 44%. And at 99.9% light speed, the universe in front of you is squeezed down to less than 4.5% of its original depth. This means that the 4.24 light-year journey to Proxima Centauri would appear to be only about 0.19 light-years at 99.9% light speed. From your perspective, you're not traveling faster than light. Instead, the distance itself has shrunk. The universe has literally become smaller in your direction of travel. This effect has been confirmed experimentally. At Stanford Linear Accelerator Center, physicists have observed that high-energy electrons behave exactly as if they're experiencing length contraction. When these electrons strike targets, the collision data only makes sense if we account for the fact that, from the electron's perspective, the accelerator is much shorter than its rest length. But here's where things get really strange. This compression only happens in your direction of travel. The universe perpendicular to your motion remains unchanged. So, as you accelerate toward light speed, the universe doesn't shrink uniformly. It gets squashed like a pancake in front of you. Spheres become ellipsoids. Cubes become thin rectangles. The familiar three-dimensional geometry of space becomes distorted in ways our brains struggle to comprehend. Imagine looking out your spacecraft window at 99.9% light speed. That planet you're approaching? It doesn't look like a sphere anymore. From your perspective, it's compressed into a thin disk. Mountains that are thousands of feet tall appear as mere bumps. Entire continents are squeezed into narrow bands, yet, if you were to slow down, everything would expand back to normal proportions. This creates a fascinating paradox that puzzled physicists for years. If you're traveling past Earth at near light speed, you see Earth compressed, but from Earth's perspective, you're the one moving, so they see your spacecraft compressed. Who's right? The answer is both of you. There's no absolute reference frame in the universe. Motion is relative, and so are its effects. This relativity of simultaneity leads to even stranger consequences. Events that appear simultaneous to you might not be simultaneous to someone else moving at a different speed. Imagine you're on a spacecraft traveling past Earth at 90% light speed. You have synchronized clocks at the front and back of your ship. From your perspective, they tick in perfect unison, but from Earth's perspective, the clock at the front of your ship is running behind the clock at the back. Events that you experience as happening at the same time are seen as happening at different times by Earth observers. The very concept of now becomes relative. There's no universal present moment that everyone agrees on. This has been demonstrated in particle physics experiments. When unstable particles called muons are created in the upper atmosphere by cosmic rays, they travel toward Earth at near light speed. These muons have such short lifespans that without time dilation and length contraction, they should decay before reaching the surface. But we detect them at ground level all the time. From the muon's perspective, it lives its normal brief life, but the atmosphere is length contracted, so it has less distance to travel. From our perspective, the muon's internal clock is running slow due to time dilation, so it lives long enough to reach the surface. Both viewpoints are equally valid and lead to the same result. We detect muons at ground level, but the strangeness doesn't stop there. As you approach light speed, the very concept of causality, the relationship between cause and effect, becomes fuzzy. In our everyday experience, causes always precede effects. You throw a ball, then it flies through the air. You flip a switch, then the light turns on, but at relativistic speeds, the order of events can appear different to different observers. Imagine you're on a spacecraft traveling at 95% light speed past a space station. You fire a laser pulse from the middle of your ship toward both ends simultaneously. From your perspective, the light reaches both ends at the same time. But from the space station's perspective, the pulse reaches the back of your ship before it reaches the front. The order of events is different. This leads to what physicists call the relativity of simultaneity. Events that are simultaneous in one reference frame may not be simultaneous in another. This isn't just a quirk of observation, it's a fundamental feature of spacetime. The universe doesn't have a master clock that everyone can agree on. Now you might be wondering, if the order of events can change depending on your reference frame, couldn't this lead to paradoxes? What if you could somehow use relativistic effects to send information into the past and create a grandfather paradox? This is where the cosmic speed limit saves us. It turns out that as long as nothing travels faster than light, causality is preserved. You can never use relativistic effects to send information into your own past. The mathematics of special relativity ensures that while different observers might disagree on the timing of events, they'll always agree on which events caused which other events. But this protection comes at a cost. It means that faster-than-light travel, if it were possible, would necessarily involve time travel and all its associated paradoxes. This is one reason why physicists are skeptical of any claims of faster-than-light phenomena. The speed of light isn't just a speed limit, it's a fundamental feature that keeps cause and effect working properly in our universe. Speaking of faster-than-light travel, let's address the elephant in the room. Science fiction is full of ways to bypass the light speed limit. Warp drives, hyperspace, wormholes, tachyons. Are any of these actually possible? The truth is both disappointing and exciting. Special relativity absolutely forbids accelerating through the light-speed barrier. But general relativity, Einstein's theory of gravity, is more flexible. It allows for exotic solutions like wormholes and Alcubierre drives that could, in principle, allow faster-than-light travel without actually exceeding light speed locally. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, is particularly interesting. It works by contracting space in front of a spacecraft and expanding it behind, creating a warp bubble that carries the ship faster than light. The ship itself never exceeds light speed relative to the space around it. Instead, space itself is doing the moving, but there's a catch. Actually, there are several catches. First, the Alcubierre drive requires exotic matter with negative energy density, something that may not even exist. Second, recent calculations suggest that creating and maintaining such a warp bubble would require more energy than exists in the entire observable universe. Third, the bubble would accumulate deadly radiation that would be released when you stop, potentially destroying anything at your destination. Wormholes face similar problems. While they're allowed by general relativity, they would likely collapse instantly unless held open by exotic matter. Even if we could create and stabilize a wormhole, it's not clear we could control where it leads. And like the Alcubierre drive, wormholes could potentially create causality paradoxes. The search for loopholes in the cosmic speed limit continues. Physicists at places like the Perimeter Institute and the Institute for Advanced Study regularly publish papers exploring new possibilities. But so far, every proposed method either requires impossible amounts of energy, depends on exotic physics that probably doesn't exist, or would create unsolvable paradoxes. This brings us back to the reality of sublight travel. Even if we can never reach light speed, getting close would still be transformative. At 99.9% light speed, you could travel to any star in our galaxy within a human lifetime from your perspective. The catch is that everyone you know on Earth would be long dead by the time you arrive. Now let's talk about something that science fiction often glosses over: what near-light speed travel would actually do to your body. The human body evolved over millions of years to function in Earth's specific environment. We're adapted to 1 g of gravity, a 24-hour day-night cycle, and protection from cosmic radiation by our planet's magnetic field and atmosphere. Take us away from these conditions, especially at relativistic speeds, and things get complicated very quickly. First, let's consider the acceleration phase. We mentioned earlier that you'd want to limit acceleration to about 1 g for comfort, but even this seemingly gentle acceleration becomes problematic over the months or years needed to reach near light speed. Your body is used to gravity pulling you downward, not pushing you backward for extended periods. The constant acceleration would feel like lying on your back with someone sitting on your chest for years. This prolonged acceleration would cause serious physiological problems. Your cardiovascular system would struggle to pump blood against the constant force. Fluid would pool in the back of your body, potentially causing dangerous swelling. Your bones and muscles, already weakened by the lack of normal gravitational stress, would deteriorate further. Astronauts on the International Space Station experience significant bone and muscle loss after just 6 months in microgravity, and they're not dealing with years of constant acceleration. But the acceleration phase is just the beginning. Once you reach cruising speed, you'd face an even more serious threat: cosmic radiation. Earth's magnetic field and atmosphere protect us from most of the high-energy particles streaming through space. But in interstellar space, traveling at near light speed, you'd be completely exposed to this radiation, and it would be far more intense than anything astronauts experience in Earth orbit. At 99.9% light speed, every proton in the interstellar medium becomes a high-energy cosmic ray from your perspective. Remember, there are about 1 to 2 hydrogen atoms per cubic centimeter in interstellar space. That might not sound like much, but when you're moving at near light speed, you're encountering billions of these particles every second. Each one hits you with the energy of a particle from a medical linear accelerator. NASA's studies of cosmic radiation exposure during Mars missions give us some idea of what this means. A round trip to Mars, taking about 2.5 years, would expose astronauts to radiation levels that significantly increase their cancer risk. But that's nothing compared to what you'd face during relativistic interstellar travel. The radiation dose would be thousands of times higher. This radiation wouldn't just increase your cancer risk, it would cause immediate radiation sickness. Your DNA would be shredded by high-energy particles. Your immune system would collapse. You'd develop severe anemia as your bone marrow stopped producing blood cells. Without massive shielding, you'd be dead within days or weeks of reaching high relativistic speeds. But let's assume we solve the radiation problem with some kind of advanced shielding. You'd still face other biological challenges that are harder to address. Your circadian rhythms, the internal biological clocks that regulate sleep, hormone production, and countless other bodily functions would be completely disrupted. On Earth, these rhythms are synchronized to our 24-hour day by exposure to sunlight. But traveling through interstellar space, you'd have no natural light cues. The stars would be distorted by relativistic effects, compressed into that bright disk ahead of you. There would be no sunrise or sunset, no natural cycle to keep your body's clock synchronized. Studies of people living in caves or isolated environments without time cues show that human circadian rhythms naturally drift to about 25 hours. Over months or years of interstellar travel, this drift would cause serious problems. Your sleep would become irregular. Your hormone levels would fluctuate wildly. Your immune system would weaken. Your mental health would deteriorate. Speaking of mental health, the psychological challenges of near-light speed travel might be even more daunting than the physical ones. Imagine being confined in a small spacecraft for years with the same few people, knowing that everyone you've ever known on Earth is aging and dying while you're gone. The isolation would be absolute. No possibility of communication with home, no rescue if something goes wrong. Astronauts on the International Space Station, despite being only 250 miles from Earth and in constant communication with mission control, still experience significant psychological stress. They report feelings of isolation, depression, and anxiety. Now imagine that same confinement, but for years instead of months, and with no possibility of returning to the world you knew. The time dilation effects would add another layer of psychological trauma. You'd know that with every day that passes on your ship, years or decades are passing on Earth. Your children would grow up, age, and die while you're gone. Your civilization might rise and fall. The very language you speak might evolve beyond recognition. You'd be traveling not just through space, but through time, becoming a stranger to your own species. But perhaps the most disturbing aspect of near-light speed travel is what it would do to your perception of reality itself. We've talked about how space contracts and time dilates, but these aren't just abstract mathematical concepts. They would fundamentally alter your experience of existence. At 99.9% light speed, your journey to Proxima Centauri would take about 35 days from your perspective. But here's the thing. Those 35 days wouldn't feel normal. The universe around you would be compressed and distorted. Time itself would be flowing differently. Your very thoughts and neural processes would be slowed down relative to the outside universe. This raises profound questions about consciousness and identity. Are you still the same person if your thoughts are running at a different rate than the rest of the universe? If you experience 35 days while the universe experiences 4 years, which time frame represents your real experience? Recent research in neuroscience suggests that our sense of time is constructed by our brains based on neural firing patterns and chemical processes. At relativistic speeds, these processes would be time-dilated along with everything else. You might not even notice that time is passing differently. Your slowed-down brain would process your slowed-down experiences at what feels like a normal rate. But this creates an eerie possibility. From the outside universe's perspective, you'd be like a person in extreme slow motion, taking years to complete a single thought. Your entire relativistic journey might appear to outside observers as a kind of suspended animation, with you barely moving or thinking for years at a time. The biological challenges don't end when you reach your destination either. If you somehow survived the journey and arrived at another star system, you'd face the problem of deceleration. Slowing down from near light speed would take just as long as speeding up, subjecting you to more years of constant deceleration forces and radiation exposure. And then there's the question of what you'd find when you arrive. The nearest potentially habitable exoplanet we know of is Proxima Centauri b, orbiting our nearest stellar neighbor. But potentially habitable doesn't mean actually habitable. The planet is tidally locked, meaning one side always faces its star, while the other is in permanent darkness. It's bombarded by stellar flares from its red dwarf star. The atmosphere, if it exists at all, might be nothing like Earth's. Even if you found a truly Earth-like planet, you'd face the challenge of biological contamination. Your body carries trillions of microorganisms that evolved on Earth. These might be harmless on Earth, but deadly to any alien life you encounter. Conversely, alien microorganisms might be deadly to you, even if they're harmless to local life. The history of human exploration on Earth shows us how devastating biological contamination can be. When Europeans first reached the Americas, they brought diseases that killed millions of indigenous people who had no immunity. The same thing could happen on an interstellar scale, but with no possibility of medical intervention or evacuation. But let's step back and consider the bigger picture. Despite all these challenges, the biological problems of near light speed travel aren't necessarily insurmountable. They're engineering problems, and humans are remarkably good at solving engineering problems when we put our minds to it. Advanced life support systems could potentially address the radiation and atmospheric challenges. Artificial gravity generated by rotating sections of the spacecraft could help with the physiological effects of prolonged acceleration. Genetic engineering or cybernetic enhancement might make humans more resilient to the stresses of relativistic travel. Some scientists have proposed that the first interstellar travelers might not be biological humans at all, but artificial intelligences or uploaded human consciousnesses. Digital beings wouldn't face the same biological constraints. They could be backed up before the journey, protecting against data corruption from radiation. They could slow down or speed up their processing to match the time dilation effects. But this raises its own questions. Would an uploaded consciousness still be human? Would it still be you? These are philosophical questions that we're only beginning to grapple with as our technology advances. One of the most heartbreaking aspects of near-light speed travel is something that science fiction rarely addresses honestly: the complete breakdown of communication with home. When you embark on a relativistic journey, you're not just leaving Earth behind physically, you're severing all ties with human civilization in ways that are both profound and permanent. Let's think about this carefully. Right now, if you wanted to call someone on the other side of Earth, your signal would take about 0.13 seconds to reach them via satellite. If you wanted to communicate with astronauts on the International Space Station, it would take about 0.0013 seconds. Even communicating with our most distant space probes takes hours, not years. But when you're traveling at near light speed to another star system, the communication delays become astronomical. A radio signal from Earth to Proxima Centauri takes 4.24 years to arrive. That means if you sent a message home when you reached Proxima Centauri and Earth immediately sent a reply, you wouldn't receive their response for 8.48 years. But here's where it gets worse. Due to time dilation, those 8.48 years of Earth time might correspond to only a few months of your time. So from your perspective, you send a message and get a reply in a few months. But that reply is describing an Earth that's nearly a decade older than when you left. Everyone you knew has aged 8.5 years in what feels like a few months to you, and that's assuming you're stationary at your destination. If you're traveling at constant near-light speed, the communication problem becomes even more severe. The Doppler effect would shift your radio signals to different frequencies. A signal you transmit at normal radio frequencies might be received on Earth as infrared radiation or even visible light, depending on your speed and direction. At 99.9% light speed approaching Earth, your radio signals would be blue-shifted by a factor of about 22. A signal you transmit at 100 MHz would be received at about 2.2 GHz. At 99.9% light speed moving away from Earth, the same signal would be red-shifted down to about 4.5 MHz. Earth would need to know exactly when to listen and at what frequency to receive your transmissions. But the frequency shift is just the beginning. The relativistic Doppler effect also affects the rate at which information is transmitted. If you're moving away from Earth at high speed, your signals arrive stretched out in time. A 1-hour message you transmit might take 22 hours to play back on Earth at normal speed. Conversely, if you're approaching Earth, your signals would arrive compressed in time. This creates a bizarre situation where the very act of communication becomes distorted by your motion. Your voice would sound like a slow, deep rumble if you're moving away, or like a high-pitched squeak if you're approaching. Digital data would need to be carefully processed to account for these time distortions. NASA's Deep Space Network, which communicates with our most distant space probes, already deals with much smaller versions of these effects. The Voyager probes, now in interstellar space, experience tiny Doppler shifts that must be corrected for. But at relativistic speeds, these effects become so extreme that normal communication protocols would be completely useless. Even if we solved the technical problems of relativistic communication, there's a deeper issue: the psychological impact of the communication delays. Imagine trying to maintain relationships with people on Earth when every conversation takes years to complete. You send a message asking how someone is doing. Years later, you receive a reply telling you about events that happened years ago from their perspective, but feel like recent history to you. By the time you receive news of a friend's wedding, their children might already be in school. By the time you hear about a parent's illness, they might have recovered or died years ago. You'd be living in a constant state of temporal displacement, always receiving outdated information about a world that's moving on without you. This communication lag would make it impossible to participate meaningfully in human civilization. You couldn't contribute to scientific discussions because by the time your ideas reached Earth, the field might have moved on. You couldn't maintain business relationships, friendships, or family connections. You'd become a ghost from the past, sending messages to a future that's already happened. But perhaps even more disturbing is what this means for the concept of shared human experience. Right now, despite our differences, all humans share the same moment in time. We're all experiencing the year 2025 together. We can discuss current events, share immediate reactions to news, and feel connected to the broader human story. At relativistic speeds, this shared experience breaks down completely. You'd be living in your own private timeline, disconnected from the rest of humanity. The events that shape your life would be different from the events shaping everyone else's. You'd become temporally isolated in a way that's hard to even imagine. This isolation would be compounded by the fact that relativistic travel is essentially a one-way journey into the future. Even if you turned around and came home, you'd return to an Earth that's decades or centuries older. The people you knew would be gone, the culture would have evolved, the very language might have changed. You'd be like Rip Van Winkle, but instead of sleeping for 20 years, you'd have been awake and conscious while the world aged around you. Recent studies of social isolation and its effects on human psychology give us some insight into what this temporal isolation might do to relativistic travelers. Humans are fundamentally social creatures. We need connection, shared experiences, and a sense of belonging to a larger community. Extended isolation leads to depression, anxiety, cognitive decline, and even physical health problems. But the isolation of relativistic travel would be unlike anything humans have ever experienced. It wouldn't just be physical isolation, it would be temporal isolation. You'd be cut off not just from other people, but from the very flow of human history. You'd be living in a bubble of slowed time, watching the universe age in fast-forward around you. This raises profound questions about the nature of human identity and consciousness. Are we defined by our relationships with others, by our participation in the ongoing human story? If so, what happens to our humanity when we're cut off from both? Some philosophers have argued that consciousness itself is fundamentally relational, that we become who we are through our interactions with others. If this is true, then the extreme isolation of relativistic travel might not just be psychologically damaging, it might actually change what it means to be human. But there's another side to this story. The isolation of relativistic travel might also offer unique opportunities for human growth and understanding. Free from the constant noise and distraction of human society, relativistic travelers might develop new forms of consciousness, new ways of understanding themselves and the universe. The great mystics and philosophers throughout history have often sought isolation as a path to enlightenment. Monks retreat to monasteries, hermits withdraw to caves. Scientists like Darwin and Einstein did their best work in relative solitude. Perhaps the ultimate isolation of relativistic travel could lead to new insights about the nature of existence itself. And there's something poetic about the idea of humans spreading out across the galaxy, each group carrying a piece of human culture and consciousness to new worlds. Even if they can't communicate effectively with each other, they'd be preserving and extending human presence throughout the cosmos. Each relativistic journey would be like planting a seed of humanity in the vast garden of space. But this brings us to another paradox of relativistic communication, the problem of cultural drift. Even if we could solve the technical challenges of staying in touch across interstellar distances, the time delays would inevitably lead to cultural divergence. Each group of relativistic travelers would develop their own customs, languages, and ways of thinking, shaped by their unique experiences and environments. Over time, these separated groups might become so different that they'd no longer be recognizably the same species, at least culturally. We see this happening on Earth over much shorter timescales. Languages evolve and diverge, cultures adapt to local conditions. What would happen to human culture when groups are separated not just by distance, but by the relativistic effects of near-light-speed travel? This cultural divergence might actually be a feature, not a bug, of interstellar expansion. Diversity has always been one of humanity's greatest strengths. Different cultures have developed different solutions to the challenges of existence. By spreading across the galaxy at relativistic speeds, humanity might evolve into a vast network of related but distinct civilizations, each adapted to their local conditions and each contributing their own unique perspective to the cosmic conversation. The speed of light isn't just a speed limit for matter and energy. It's the speed at which information can travel, the rate at which cause and effect propagate through space-time. This creates what physicists call light cones, regions of space-time that can influence each other. Events outside your light cone cannot affect you, and you cannot affect them. This fundamental structure of reality means that the universe is naturally divided into regions that are causally disconnected from each other. Think about what this means on a cosmic scale. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, has a radius of about 46 billion light-years. But there's almost certainly more universe beyond what we can see. In fact, if current theories about cosmic inflation are correct, the total universe might be vastly larger than the observable portion, possibly even infinite. This means there could be countless other civilizations out there, separated from us not just by distance, but by the fundamental structure of space-time itself. Even if they developed faster than light travel tomorrow, we might never know about each other because we're outside each other's light cones. The universe might be teeming with life and intelligence, but the cosmic speed limit ensures that most of it remains forever hidden from us. But here's where the story takes a fascinating turn. While the speed of light creates barriers, it also creates opportunities. The time dilation effects that make relativistic travel so challenging for maintaining connections with home also make it possible to explore vast distances within a human lifetime. From the traveler's perspective, the entire observable universe becomes accessible. At constant acceleration of 1g, you could reach the center of our galaxy in about 20 years of ship time, even though the journey would take 26,000 years from Earth's perspective. You could travel to the Andromeda galaxy in about 35 years of ship time, though Earth would experience 2.5 million years. In principle, you could explore the entire observable universe within a single human lifetime, at least from your own reference frame. This creates a profound asymmetry in the universe. While civilizations remain isolated from each other by the cosmic speed limit, individual explorers can potentially visit multiple civilizations within their own lifetimes. You could be a cosmic ambassador carrying news and knowledge between worlds that could never communicate directly with each other. Imagine the stories you could tell. You might visit a world where civilization is just beginning to develop agriculture, then travel to another where they've already colonized their entire star system. You could witness the birth and death of stars, the formation and collision of galaxies, the evolution of life on countless worlds. You'd become a living library of cosmic history, carrying the memories of civilizations across the vast expanses of space and time. But this cosmic perspective comes with a price. You'd also witness the inevitable end of everything you've ever known. Stars burn out. Galaxies drift apart. Even protons might eventually decay given enough time. The universe itself is expanding and cooling, heading toward what cosmologists call the heat death, a state of maximum entropy where no more work can be done and no more complexity can emerge. Recent observations from the James Webb Space Telescope and other instruments have confirmed that the expansion of the universe is accelerating, driven by something we call dark energy. This means that distant galaxies are moving away from us faster and faster. Eventually, they'll be moving away so fast that light from them can never reach us. The observable universe will shrink, leaving us isolated in an ever smaller island of visible matter. For relativistic travelers, this cosmic perspective would be even more dramatic. Due to time dilation, you'd experience the universe's evolution in fast forward. You might watch entire stellar life cycles play out during your journey. You could see galaxies collide and merge, witness the formation of new stars and the death of old ones, and observe the long-term evolution of cosmic structure itself. This raises profound questions about the meaning and purpose of existence in a universe governed by relativistic physics. If every journey takes you further into the future, if every exploration separates you more completely from your origins, what's the point of the journey? Why explore a universe that you can never truly return to share your discoveries with? Perhaps the answer lies in the journey itself. The universe has spent 13.8 billion years evolving from a hot, dense state to the complex, structured cosmos we see today. Stars have formed and died, creating the heavy elements necessary for planets and life. Galaxies have grown and evolved, creating the conditions for stellar formation and planetary systems. Life has emerged and evolved, eventually giving rise to consciousness and intelligence. We are the universe becoming aware of itself. Through our eyes, the cosmos observes its own beauty and complexity. Through our minds, it contemplates its own existence and meaning. We are not separate from the universe. We are part of it, the part that can think and wonder and explore. From this perspective, relativistic travel isn't just about getting from one place to another. It's about extending the universe's capacity for self-awareness across space and time. Every journey, every exploration, every moment of wonder and discovery adds to the universe's understanding of itself. Even if the traveler can never return to share their discoveries, the act of discovery itself has value. This cosmic perspective also helps us understand why the universe might be structured the way it is. The speed of light limit ensures that the universe remains diverse and interesting. If faster than light travel were easy, everything would quickly homogenize. Cultures would merge, knowledge would spread instantly, and the rich diversity of cosmic evolution would be lost. Instead, the cosmic speed limit preserves diversity. It ensures that different regions of the universe can evolve independently, developing their own unique characteristics and solutions to the challenges of existence. It creates a universe that's not just vast in space, but rich in possibility and variation. Recent research in astrobiology and the search for extraterrestrial intelligence has begun to appreciate this diversity. The Kepler Space Telescope and other planet-hunting missions have shown us that planetary systems come in an amazing variety of configurations. Some have hot Jupiters orbiting close to their stars. Others have super-Earths with no analog in our solar system. Some orbit binary stars or exist in complex multi-star systems. Each of these different environments might give rise to different forms of life, different evolutionary pathways, different solutions to the challenges of existence. The cosmic speed limit ensures that these different experiments in life and intelligence can proceed independently, creating a universe that's not just alive, but vibrantly diverse in its aliveness. But perhaps the most profound implication of relativistic physics is what it tells us about the nature of time itself. In our everyday experience, time seems to flow uniformly from past to future. We remember the past, experience the present, and anticipate the future. But relativity shows us that this is just one perspective on a more complex reality. From the universe's perspective, all of space-time exists simultaneously. Past, present, and future are all equally real, just different regions of the four-dimensional space-time continuum. Your birth, your life, your death, and everything that happens after you're gone all exist together in the eternal structure of space-time. This view, sometimes called the block universe or eternalism, suggests that time doesn't really flow. We just experience it that way because of how our consciousness moves through the space-time continuum. From this perspective, relativistic travelers aren't really traveling into the future. They're just taking a different path through the eternal structure of space-time. This has profound implications for how we think about mortality and meaning. If all moments in time are equally real, then nothing is ever truly lost. Every moment of joy, every discovery, every act of love and creativity exists forever in the structure of space-time. Death isn't an ending, It's just the boundary of your particular path through the eternal cosmos. Let's imagine for a moment that humanity does eventually develop the technology for near light-speed travel. Perhaps we discover new physics that allows us to generate the enormous energies required. Maybe we develop fusion rockets or antimatter drives that can sustain acceleration for years. Or perhaps we find ways to upload human consciousness into digital forms that can better withstand the rigors of relativistic travel. What would such a future look like? Picture this. In the year 2100, the first relativistic expedition departs Earth for Proxima Centauri. The crew, enhanced with genetic modifications and cybernetic implants to survive the journey, accelerates away from our solar system at a steady 1G. From their perspective, the 4.24 light-year journey takes about 3.5 years. But when they arrive, Earth has aged 4.5 years. They find Proxima Centauri b to be a harsh, tidally locked world, bombarded by stellar flares. But in the shadow zone between the day and night sides, they discover something extraordinary. Microbial life, unlike anything on Earth, thriving in conditions that would be lethal to terrestrial organisms. They spend several years studying this alien biosphere, making discoveries that revolutionize our understanding of life itself. When they finally send their data back to Earth, the transmission takes 4.24 years to arrive. By the time Earth receives their discoveries, the expedition has been gone for over a decade. The scientists who planned the mission have retired. The technology used to build their ship is obsolete. The world has moved on. But the discoveries themselves are transformative. The alien microbes use a completely different biochemistry, based on silicon rather than carbon. They derive energy from the planet's magnetic field rather than chemical reactions. They reproduce in ways that challenge our very definition of life. These discoveries spark a revolution in biology, leading to new technologies, new medicines, new ways of understanding the universe. Meanwhile, the expedition faces a choice. They can return to Earth, knowing they'll arrive to find a world that's aged 20 years in their absence. Or they can continue onward, becoming permanent nomads in the cosmic ocean, carrying human consciousness to new worlds and new discoveries. Some choose to return, becoming living bridges between Earth and the stars. They bring back not just data, but stories, perspectives, and wisdom gained from their unique journey through space-time. They become teachers and philosophers, helping humanity understand what it means to be a spacefaring species. Others choose to continue the journey. They become the first of a new kind of human, the relativistic nomads, forever traveling between the stars, forever exploring, forever discovering. They form a loose network of explorers, occasionally meeting at stellar waypoints to share knowledge and stories before continuing on their separate paths. Over the centuries, this network grows. Relativistic travelers spread throughout the galaxy, each carrying a piece of human culture and consciousness to new worlds. They discover planets with vast oceans beneath ice shelves, worlds where life has evolved in the atmospheres of gas giants, ancient civilizations that died out millions of years ago, and young worlds where life is just beginning to stir. Each discovery adds to humanity's understanding of the universe. Each journey expands the boundaries of human experience. The relativistic nomads become living libraries carrying the accumulated wisdom of countless worlds and civilizations. They are no longer quite human in the traditional sense, but they are something more. Cosmic citizens, children of the universe itself. But this future comes with costs. The relativistic nomads become increasingly isolated from their origins. Earth becomes a distant memory, then a legend, then a myth. The nomads develop their own cultures, their own languages, their own ways of understanding reality. They remain connected by their shared human heritage, but they diverge in ways that would make them almost unrecognizable to their ancestors. Some nomads choose to settle on worlds they discover, founding new civilizations that blend human culture with local conditions. These settlements become stepping stones for future explorers, but they also become isolated from each other by the vast distances and time delays of interstellar space. Humanity fragments into countless separate branches, each adapted to their local environment, each following their own evolutionary path. This fragmentation might seem tragic, but it's also beautiful. It represents the ultimate flowering of human potential, the spread of consciousness and intelligence throughout the galaxy. Each branch of humanity becomes an experiment in what it means to be alive, to be aware, to be part of the cosmic story. And through it all, the universe continues its own evolution. Stars are born and die. Galaxies collide and merge. The cosmic web of dark matter continues to grow and evolve. The relativistic nomads witness this evolution firsthand, becoming chroniclers of cosmic history on scales that dwarf human civilization. Some nomads choose to journey to the very edge of the observable universe, riding the expansion of space itself to witness the birth of the first stars and galaxies. Others dive deep into the galactic center, studying the supermassive black holes that anchor galactic structure. Still others seek out the dark matter filaments that connect galaxies, searching for clues about the universe's ultimate fate. Through their journeys, humanity becomes something unprecedented in cosmic history, a species that has transcended its planetary origins to become truly cosmic in scope. We become witnesses to the universe's grandest stories, participants in its deepest mysteries, guardians of its most precious gift, consciousness itself. But perhaps the most profound realization that emerges from this cosmic perspective is that the journey itself is the destination. The universe doesn't have a purpose in the traditional sense, it simply is, unfolding according to the laws of physics, evolving from simplicity to complexity, from uniformity to diversity, from unconsciousness to awareness. We are part of that unfolding. Every moment of wonder, every discovery, every act of love and creativity adds to the universe's richness and complexity. We don't need to reach some final destination or achieve some ultimate goal. The very fact that we exist, that we can think and feel and explore, is itself a victory against the forces of entropy and decay. The speed of light, which seemed like such a limitation at the beginning of our journey, reveals itself to be a gift. It ensures that the universe remains vast and mysterious, full of unexplored regions and undiscovered wonders. It preserves the diversity that makes existence interesting and meaningful. It creates the very structure of space-time that allows for the complex dance of matter and energy that we call life. So what would really happen if you traveled at light speed? You would discover that you are already traveling through space-time at the speed of light. We all are. We're just moving mostly through time rather than space. Every second that passes, you travel 1 second into the future. Every moment of your life is a journey through the four-dimensional landscape of space-time. The question isn't whether you can travel at light speed. You already are. The question is how you choose to navigate the cosmic ocean of space and time. Will you remain anchored to one small world, or will you set sail for distant shores? Will you be content with the familiar, or will you seek out the strange and wonderful? The universe is vast beyond imagination, filled with wonders we can barely conceive. It's a place where time can slow down and space can contract, where the very fabric of reality bends and warps, where consciousness can emerge from unconscious matter and contemplate its own existence. It's a place where every journey is an adventure, every discovery is a revelation, every moment is a miracle. You are made of stardust, forged in the nuclear furnaces of ancient suns, assembled by billions of years of cosmic evolution into a being capable of wonder and understanding. You are the universe becoming aware of itself, a temporary arrangement of matter and energy that can think and feel and dream. Whether you travel to distant stars or remain on Earth, whether you live for decades or centuries, whether you discover new worlds or simply appreciate the one you're on, you are part of the greatest story ever told. The story of a universe that began in simplicity and evolved into complexity, that started with nothing but energy and space and time and somehow, impossibly, beautifully, gave rise to you. That is the real answer to what happens when you travel at light speed. You discover that you are already on the most incredible journey possible, the journey of existence itself, unfolding moment by moment in the vast cosmic theater of space-time. And that journey, my fellow traveler, is just beginning. And if you enjoyed this video, I am sure you are going to love this other one on the left side of the screen. Why nothing can go faster than the speed of light. This video is for you if you're fascinated by the speed of light, relativity, and the mysteries of space and time. See you there.